So Clara and I will talk about a way to manage IVV using model-based system engineering. So we work in Thales Elancourt in France and in a business line dealing with optronic and secure equipments. So the presentation will be organized in two main parts. First, I will do a little introduction explaining the kind of system we are developing, which has are embedded systems, and the main principles we want to deploy concerning model-based system engineering pulled by IVV. And in a second part, Clara will go in more details to show you the tooled process we have defined based on the RMIVV add-on, which is a Capella add-on. So our business unit designs and produces airborne defense equipment. So we have two main of them. I said seekers and surveillance or designation pods. I will focus on this last systems since they are facing to increasing complexity because the systems are, even if they are embedded equipments, they manage several optical channels with several types of high resolution sensors. And there is a strong need of intensive image processing inside, so quite like high performance computing, but embedded. But it is highly constrained by volume and power consumption. So the design implies many disciplines to build the system, including optics, electronics, mechanics, thermics, software, and firmware. So you can see on the right of the slide two examples of systems, one surveillance on the top and one system Thales of designation. And on the bottom, you can see some images that can be captured during missions. So even if our legacy products are in development since 15 years today, we are facing to many evolutions, functional evolutions, and introduction of new capabilities, such as pilot-assisted detection or recognition and identification of targets. So it will introduce artificial intelligence, for instance. So in terms of hardware, it will imply to integrate more sensors, more hardware platforms, boards, heterogeneous processors, or co-processing, to be able to integrate all of these functions, new functions. We will certainly have to integrate the both two-in-one surveillance and designation in the same product, which is not the case today, and introduce artificial intelligence. So this will be in the same envelope of volume and thermal. So it's a very strong challenge for us. And we strongly believe that model-based system engineering will help us to master this complexity and the multidisciplinary coherence. So to meet these challenges, this goal, we have introduced improvement in the co-engineering. So to improve cross-disciplinary cooperation, we implemented a more structured co-engineering principles, which goal is to move from siloed document-centric practices to a more cooperative model-centric engineering. To achieve this, we implement lean-inspired approaches, and these approaches are supported by a range of tools. So the first driver is iterative and incremental development, which is the main driver to reach an engineering based on pool scheduling. Another aspect important is the collective production of documentations, since it will allow to avoid siloed effects and to have more cooperative work between disciplines. And also, the search of global optimum is something important, since today it's more optimum locally that is done by discipline or by services. And all of that, of course, shall be synchronized with activities like agile rituals that are well known in the industry. So if we focus on model-based system engineering applied to this co-engineering approach, the artifacts that we manipulate with the Arcadia method are essential to this co-engineering drivers, since functional chains are the basis to define incremental development. So the development increments are defined based on the functional chains. Functional chain and capabilities are also important because they are the value for the customer. So it's an important driver for the value-driven flow. Concerning documentation, instead of having document templates and doing copy-paste from diagrams in the models to the document, the goal is to structure the specifications based on the structure of the model and produce the documentation based on the model. And finally, the global optimum shall be reached since the model shall be the reference for all disciplines and shall be the cooperative way to manage the different teams and disciplines by co-constructions of the different level of models, system or subsystems. Few definitions now. What is a development increment for us? The incremental development is driven by, as I said, the clear definition of functional chains. So an increment in our vision is it corresponds to a deliverable that brings value to the one we will consume it. So it's true for all the levels at system level, subsystem, hardware, software. The increment shall be testable in order to be deliverable to the. It shall bring value. And it is deduced from the system analysis. So we define it at a need level in the Arcadia perspective, and it is refined at the logical and physical architecture. We will see that later, and we will see that we have two strategies to build increments based on system analysis. The next definition is more a major shift compared to what we did in the past, since we try to involve IVV as early as possible in the modeling phases activities, so that they can take ownership of the functional chains which are defined with the architect. So we do not wait for the second part of the V to involve the IVV manager. In fact, it is from the functional chains that are broken down into logical architecture and physical architecture that the IVV will be able to identify scenarios that will be dedicated for testing its release, for instance. And since he will have an early knowledge of the model, he will be able to contribute to the breakdown of these development increments and bringing out the needs in terms of observability in the model, which is very important for IVV, and by identifying enabling systems and as early as possible. So just the two examples of ways to define increments. The first one, so if we consider that we have to deliver a release to a customer, we consider a capability at system analysis level, which is at the need perspective of Arcadia. So it's very simple. We have a capability with one functional chain. And on the right, you can see this functional chain is crossing the system through two functions. When we identify development increments at solution level, so on the next yes, at physical level, you can see that this functional chain from system analysis has been refined in the physical architecture in two subsystems, and it crosses from the same actor to the same actor, the full system. The strategy here is to say that we will develop a first increment based on the component subsystem 2, since perhaps all the hardware and the teams are available to develop it. Perhaps subsystem 1, we have issues of approvisioning materials or things like that. So the strategy, the decision is to develop the second subsystem. So sorry. So if we develop this increment, this first increment, it means that it is needed to identify observability points to be able to stress this subsystem during the IVV. And then in a second step, we will develop the second increment, which is in yellow and cross the subsystem 1, and will be integrated with the subsystem 2. The next way, the second approach that can be used for defining increments, if we start from the same perspective, system analysis at need level, is to decide that the first increment will be the full end-to-end functional chain that will cross the full system over subsystem 1 and 2. But we will focus only on functional aspects. For instance, we could imagine that we want to show the quality of image, starting from the sensor to the display of the system, and showing that our algorithms are efficient and show a good image. But we do not care about real-time aspects. If we lose some images, or if latencies are not so good, it's not an issue for this first increment. And the second increment is will enrich the first one by adding these quality attributes, non-functional aspects, with a better robustness of the functional chain to address real-time and latencies. So this is the second way to define it. So I finished my introduction, and now Clara will present you in more detail how we can manage these theoretical aspects I presented in using RMIVV in Capella. So Clara.
Thank you. Good morning or good afternoon, everyone. Thank you, Olivier, for this introduction, which allows me to dive straight into the heart of the matter, which is how to define increments. Over the next 30 minutes, my goal is to convince you of the benefits of defining increments with Capella. So I'll start with the basics, and I think you have to ask yourself, what is an increment? Let's imagine you want to build a car. This project is too complex to develop all at once. So we divide the project into smaller parts called increments. Each increment is a step of the project. So to understand how we define an increment more clearly, let's continue with the example of the car. To define each part, we start by identifying something that is required. For example, we are required to make the engine. Once we know that, we need to figure out everything that needs to be developed. What material are needed, the size and the specifications, and the necessary features, for example. Therefore, each increment involves two major steps of reflection. The step one is define what is required, and the step two is deduce what needs to be developed. To simplify with simple terms, define what is required means identify the need, while deduce what we are going to develop means finding the solution. If you are familiar with Capella and especially with the Arcadia method, I believe that those two words have a meaning for you. And that will be normal because these are the two main categories of layers that you will find in Capella. So when you define the need for an increment, we work in the layer of need, so OA and SA. This step is very important, especially at Thales, because we try to meet the need of our customers. And with each increment, our goal is to deliver something of value to our customers. And to deduce what needs to be developed, we move on the solution layers, so the LA and PA. It's in these layers that we find the breakdown of the system into logical and physical elements. So we took stock of the current situation. We have two processes. The creation of a model in Capella. This is the job of the project team. They create a graphical view of the system, which help to visualize things better. And then the definition of increments. That's where the project manager comes in. They tend to have a more temporal perspective of the project, focusing on timelines and milestones. So we have observed the link between these two processes because they share common concepts, the need and the solution. And this led us to the conclusion that in our model-centric approach, it makes sense to define increments directly in Capella. This way, we don't have to create new elements, but simply reuse existing ones in the model. And this opportunity enabled us to discover that Thales had developed an add-on called RMIVV, especially designed to facilitate the creation of increments in Capella. What RMIVV stands for? It's for Release Management and IVV. And the purpose of this add-on is twofold. First, we have release management. It's to simplify increment creation and management. So here we can find our two steps we talked about earlier. And when we develop the product, we go through three key stages, defining the needs, the development, and the product testing. An increment must be testable. And in our new approach, we involve IVV activities from the start using the RMIVV tool to ensure testability of the increment. So I will come back to this point later in the presentation. For the moment, we are simply introducing the tool and an overview of our approach. So as you will see, this tool, like many others, offers many features. There are some elements I wouldn't cover today, but we quickly saw its potential. So we had to define a strict process to avoid getting lost in it. To recap, here is an overview of the key stage in defining the increment. First, we identifying the requested element. Then we deduce what needs to be developed. And finally, we evaluate the testability and adjust the need if it's necessary. Keep this recap in mind as we'll be adding it to it as the presentation progresses. So let's move on the detailed explanation of the process. I'll show you how it works with a case study so you can get a better idea. Let's imagine that an IVV manager, together with the co-engineering team, is faced with the task of defining increments in Capella. Here, our IVV manager knows how to use Capella. But with this case study, we'll go through various steps and see how the RMIVV can simplify this task. The project used is the PITA drone. It's a drone with three surveillance missions in three different environments. However, Keep in mind that we are still working on the process we're presenting today. It's still being testing on project, and we can claim that we have the final solution. But we already have a good idea of the steps we are about to present. So our IVV manager received the release identified by the PDA, who is the chief engineer. A release is the functionalities that will be present to the customer. The key thing to remember here is that a release is a major version expected by either by the customer or internally by the project, and it's the input for defining increments. So the IVV manager receives uh, his email, and he will see that the chief engineer choose one capability as the boundary of the release. She could have choose something else. There is no limitation with the tool, but this makes sense to us because a capability at the SA level is a customer need. The capability here is manually acquire data. Once received, the IVV manager must identify the release. It's in the step 0 because it takes place before the utilization of RMIVV. It's a preliminary step, for example, I think. To do this, the IVV manager opens Capella model and search from its capabilities. It doesn't know the model by heart, so it will use the search tool to find it quickly. Once found, it identifies the functional chains to be developed. Why a functional chain, we will say me? Because they have value for the customers and meet requirements. So with that, it was appropriate to work at this level of granularity. So the functional chains are here. Once the chains are identified, our IVV manager has to check if the project complies with the design rules. It's because we realize that the RMIVV add-on use realization links between elements, and if links between elements are missing, the software will generate false results. Therefore, we create VIATRA rules to inform us about possible omissions. We call these rules verification rules. VIATRA, for those who don't know, is a Capella plugin lets you create filters on Capella model elements and their properties. Especially, a rule is a sequence of filters that can contain simple calculation. That's how we use it, but VIATRA can do many other things. What you need to know is that VIATRA rules generate for us, for example, an array with the problematic elements. And I won't go into today in details because it's not a VIATRA presentation, but this plugin developed by Inquiry Labs is well documented online. So our IVV manager will launch one of the verification rules. Here we can see links that might be missing just after. Here that the link that may be missing. And if lines appears in the results, it indicates that an element is missing required upstream or downstream link. In this case, the IVV manager will notify the model architect and request that the necessary correction be made. Once the model have been reviewed and found to be complete, the IVV manager will analyze the model to determine the order in which the chain, would be developed. There are several ways of doing this. First, it will look at the model diagram, but we found that a more global view of the project was missing, so that the IVV manager couldn't compare the chain. So to that end, we have created other VIATRA rules. Here we call them analysis rules. So the IVV manager will launch one of the rules. Here, the rule have already been configured. It launched the ASA level rule. Thanks to this rule, we can see the chain with core functions here. And we can see also that, for example, in the chain, this one, mainly trigger 3D image acquisition. The first two functions are also present in other chains, and they are in subchains. So with this step, our IVV manager has a first idea of the order he could give to his increments. He proposed, for example, to start with the chain manually HD trigger HD video acquisition. So the IVV manager has just finished up the preliminary task in preparing for using RMIVV. Okay, let's get to the point. We've gone over the three main theoretical steps we're defining on the increments. So how does this step fit into our RMIVV? So the first thing to know is that we start by using the notion of version to organize and track the steps. A version is an array where we insert model elements. There are two types of version, each corresponding to the first two steps of the process. Let's start with the step one version is the requested version. So this is where we enter all the elements related to the identify requested elements. In this case, as we said before, our need is a functional chain from the assay level, system analysis level. So what our manager has to do is create the RV version. I will start by initializing the tool by adding the necessary tabs. As you can see, we will see, this part of the tool is very intuitive. We create our requested version and the array I mentioned earlier appear. He will rename it, for example, RV1, and then fill it by dragging and dropping our first functional chain. Now that we have defined the need, let's move on to step two. We'll figure out the solution. So we are going to use the second type of version, the developed version. This time, the IVV manager doesn't create a new empty version. Instead, he will generate it from the requested version. And once again, the process is both quick and simple. The RMIVV add-on will ensure that we do not overlook any functions or components and will provide us the results in 10 seconds, which would overtake an hour to analyze and record. How does it work? The add-on will follow the realization link here, um, and that originates from the functional chain and insert the function chain, insert in the RV, in the requested version. And you will then identify any LA NPA level function and components that follow these links and provide this information to us in the generated developed version here. So it's therefore important to check the model before, as any missing link will result in the omission of one or more function or component. When we take a quick look at the elements, the IVV manager, thanks to his expertise, identified that certain information in function, cannot be developed or tested at the same time. This is because RMIVV and Capella are not aware of the company constraints, which may be the number of bench available, number of team available, the working if the work is internal or external. So the IVV manager with the co-engineering team must use his knowledge of constraints to divide up the developed version. Now we begin to construct our increments, which we refer to as a developed version. But we now designate this as developed version real. A developed version real is a piece of the developed version theoric. The difference is that the developed version real is not generated by the tool. It's created from an empty developed version. into which we insert elements of our developed version theoric. So here, our IVV manager creates our first developed version real. So, but before he can fill it, he must first analyze the function and compare them. Capella provides a variety of tools to assist with this process, including the mass visualization view, which enable comparison of the properties associated with each function. And subsequently, we can access to the semantic browser to examine the diagram or functional chain associated with each functions. For a better organization, he can rename his version as he wish. So we can see he renamed the different versions. And after conducting his analysis of and considering the company constraints, the IVV manager decides to create 3 increments with the chain manually trigger HD video acquisition. It will create, rename, and populate his developed version real. So it's the DV 1.1, 1.2, and 1.3. He then utilize a diagram that illustrates all the functions of the developed version theoretical. So insert, I will explain this functionality after. So the developed version real, it's the one which is generated from the requested version, I repeat. And to populate is developed version real. This is one method, but the diagram if the diagram doesn't exist, you can simply use the version array or mass visualization view, for example. So the other method for analyzing version is the diagram colorization we can see here. It's a tool provided by RMIVV. And this method allows users to colorize elements in one or more specific diagrams. To use this feature, the IVV manager opens the diagram of interest and inserts the different version. So the tool will automatically color the elements from the same version with the same color. And as the IVV manager say, the version can be leaked temporarily. I don't have the time to explain all the functionalities, but okay. And you can also enter the maturity of an element as a function of its version. So here there is a possibility to enter the maturity of the elements. So and there is one more step to consider, and that's the testability. So our step 3, and well, RMIVV simply look at the elements that have exchanged with others function or components. These are the elements that needs to be blocked, simulate, or developed before testing. This category is called enabling system. As with version, the elements appear in an array, but we cannot state this is a version. It's rather a parallel concept. It assesses to external boundary of the increments, a bit like stakeholders of the increments. So our IVV manager will generate our ES 1.1 from the DV real 1.1 and repeat for the step for ES 1.2 and 1.3. And this element found in the enabling system have a link with the elements in the associated DV real and are therefore present in the LA and PL layers. This link may be a functional exchange or allocation, but it's not a realization link between elements. These elements are not present in the DV real, either because they do not originate from the functional chain in the RV, requested version, or because they are present in another developed version real. So there are the project constraints. We can show the the element in the diagram just here. He had the ES version, and in this PAB, he display so the GV real 1.1 in purple and the enabling system associated in blue. Now our IVV manager has all the tools and methods it needs to analyze the model and then modify the increments, which are, I remind you, in our developed version real. Here, our IVV manager can take into account both company and project constraints. And in conclusion, um, the RMIVV add-on has a great potential for development and integration activities. It's help identify elements to develop and encourage collaboration between architect and IVV responsible. It's also provide efficient tools for managing release and increments with better visibility through diagrams, colorization, and the ability to export data to other tools. However, there are still some limitations to address, such as transition RMIVV RVs and DVs into subsystem models, integrating with Polarion, and answering DVs are recalculated when an RV is modified. If you need more information, you can contact us at these emails, and thank you for your attention.
Thank you very much, Clara and Olivier, for a very detailed and insightful presentation. Great demos. So we now have time for a few questions. I see system and subsystem on slide 4. Is the Capella setup that is in use having libraries for the subsystems?
You mean libraries in terms of Capella libraries, I guess?
I suppose yes.
Yeah. In our approach, for instance, for the moment, we are dealing with proof of concepts. So, as said, Clara, it's not done yet in real project. We prepare the future since we will have a new project. So we do not use libraries, but this is something we would like to do to manage, especially data models or interfaces that we would like to reuse from a product to another product. I don't know if it answers the question.
Yeah, I think it does. Thank you, Olivier. Next question. Is the RMIVV tool available to the public? Would love to try it out.
So today it is not. It's an add-on developed by Thales. So don't hesitate to send me an email so I can transfer it to the central teams that are working on it in Thales, since we are a business line using it. But it should be possible. I asked it before the presentation. I'm not sure of the conditions to use it, so send me an email and I will transfer it without no problem.
Thank you, Olivier. Next question. When developing a new variant of system, it is common in concurrent engineering to have multiple changes on functions in the different areas of the system. Does this mean to have a release for every change?
We didn't address these aspects concerning the management of variants. We are exploring more featuring. Don't remember the name of filtering add-on to manage variability in the models, or the pure variant add-on, and we guess that it is not today compatible with the RMIVV add-on, since we have seen that RMIVV add-on is not compatible with the system to subsystem. It's certainly necessary to extend it to manage variabilities in the system.
Thank you. And next question. How do you integrate your presented release management approach with leading industrial PLM platforms from Siemens, PTC, SAP, and others with their strong focus on configurations and respective system life cycles?
As said Clara, as a conclusion, today it's not the artifacts that are produced by RMIVV are not importable in tools like Polarion, for instance, to manage work items. So this is something we have to work on. Today we envisage using tools like Jira to manage this kind of artifacts, but clearly, as I said, we are in experimentations and these questions are not completely addressed today, but it's a good question that we will address in the coming months.
Maybe a quick question on my end. So I understand that you are preparing the future projects, and I also understood that you are doing some experimentation. So can you elaborate maybe a little bit on the first feedbacks you are receiving from the initial experimentation of these new ways of doing things?
Yeah.
If you have some feedback.
Yeah. So first, we have done proof of concept mini projects based on real products. So this is products that will be developed in the coming 2 or 3 years. So the start of the development will start around 2026 or 7. So we prepare that, as I said, preparing a new engineering approaches. And the first feedback of an IVV manager which managed this proof of concept is that first is very happy to be early introduced in the model-based system engineering phases at the very beginning, since in the past project it was not the case, and he really appreciates to have a view of the architecture and of the needs, even at system analysis level. And secondly, the RMIVV add-on is really a good candidate for him to address releases and development increments, even with the limitations we have explained. So it's really something we would like to be able to deploy, but we hope that limitations will be addressed, since we want to use system to subsystem transition. It's important for us regarding the complexity of our system.
Thank you, Olivier. Maybe we have time for one more question. And so maybe a similar question that the one we had in the present presentation. When specifying the physical architecture, how do you determine the optimal level of detail to include in the model, and how is the model specification linked to the domain specified design artifacts like PCBA, schematics, salary CAD, etc.?
I haven't seen
It's a little bit outside of the scope of this presentation, but I don't know if you've got an answer on that.
So the criteria for physical architecture is first to stop at the level of the IVV discipline can manage. So it means that system level, we should not go in more detail than subsystem in black box, and the system will specify the perimeter of these subsystems to the next discipline. And we envisage to build subsystems for each, for instance, the sensor part and or the processing parts, which are two main subsystems, will be developed in new models based on the physical architecture from the system level. So we do not go in detailed detailed design in the physical architecture. The goal is to have the main breakdown of the system and the interfaces well defined between the sub-elements, the components. The internal of the components are done by software modelization in software or by using Simulink or things like that.